we were discussing calculation of mass percent and mole percent. So now let's look at a more difficult or slightly more involved example where we're asked to calculate the mole percent of each element given the name. So I'm telling you that this is dioxygen difluoride. It's quite a reactive species with very interesting properties and reactivity. With that said, what I would like you to do is to write out a valid formula given the name and then calculate the mole percent. As we're still developing our nomenclature skills, and I really want to make sure we're focusing on the mole percent calculations rather than agonizing over the nomenclature, let's try to figure out the formula together. So dioxygen difluoride. So what type of compound is this? Ionic or covalent? Covalent. You see these di prefixes? That's signifying we are dealing with a covalent compound. So dioxygen, what does the di prefix signify? 2. So this is F2. Oh, well, O2 for oxygen. And then how many fluorines do we have? 2. Okay, perfect. So from this information, what I want you to do is to calculate the mole percent, and then as well, I want you to calculate the mass percent of each element. I'm going to set up the document cam. Give me one moment, and I'll be walking around to check to see how everyone's doing. Okay, I'll be walking around and checking to see how everyone's doing. Mole percent and mass percent. Everything going okay? Everything going okay? For the mole percent? Oh, how many moles of oxygen do we have? How many oxygen? Yeah. But looking at your calculation. Okay. Yeah. Oh, but like you plugged in how many moles of oxygen? Oh my God. Everything going okay?
So once I have,
yeah. Oh, that would be for the mass percent. So start with mole percent. And then for mass percent, yes, you take the mass of the total. So I see a lot of reasonable answers for the mole percent. So let's talk a little bit about this. So first things first, we have how many moles of oxygen? How many moles of oxygen do we see? 2. How many moles of fluorine do we see in this chemical formula? 2. Okay, so in total, 2 plus 2 is 4 moles. Okay, from here, we can calculate the mole percent of each element. So if we want to calculate the mole percentage of oxygen, we have how many moles of oxygen? 2. So we have 2 moles of oxygen, and we have how many total moles? 4. Okay, so 2 over 4 times 100% gives us a mole percent of 50%. Without even doing any calculations, we can also figure out the mole percentage of fluorine. What would you expect the mole percentage of fluorine to be? 50%. Both mole percentages, if you're accounting for all elements and all species in a compound, will add up to 100%. So the mole percentage of fluorine is equal to 2 moles of fluorine over 4 moles times 100%, and that in turn gives us 50%. Perfect. Now, I asked you to calculate the mass percent, and I've set up these problem sheets in a way that we can calculate the mass percent on a separate sheet. Is everyone comfortable with the mole percentage calculation so far? Okay, so let's move on to mass percent now. So we've previously established this is F2O2. We have 2 moles of oxygen, and we have 2 moles of fluorine. Let's now get to work and figure out the masses. So if we have 2 moles of oxygen, what is the mass of oxygen? How many grams are present in a mole? 16. So we're going to plug in 16.0 grams of oxygen per every 1 mole of oxygen, which in turn gives us 32.0 grams of oxygen. Perfect. Let's do the same thing for fluorine. Let's repeat this process for fluorine. What is the atomic mass of fluorine in the periodic table? 19. So we have about 19.0 grams of fluorine per every 1 mole of fluorine. And this we can do without a calculator, but you're welcome to plug it into the calculator. We have 38.0 grams of fluorine present in the sample. If we add up each of these masses together, 38 plus 32, we have 70 grams total per mole of F2O2. Just the same way that we calculated our molar masses. So whenever you calculate a molar mass, if I'm asking for mass percent and mole percent, pay attention to your setup. So that way you can save yourself a little bit of time. Okay, we're now ready to calculate the mass percentage. So let's do just that. So the mass percentage of oxygen, what is the total mass of oxygen in our sample? 32, yep. So we have 32.0 grams, and we have 70.0 grams total times 100%. Everyone's comfortable punching this into the calculator, right? Okay, so let's just do that. 32 divided by 70 times 100, and that in turn gives us 45.7%. Again, without doing any additional calculations, we would expect our mass percentage of fluorine to be around what value? About 54, yeah. 54.3 if we're going to be exact. So let's check to see how that works out. So the mass percentage of fluorine, we plug in 38.0 grams over 70.0 grams total times 100%. Notice grams over grams, the units cancel. Percentage is a unitless number. So we have 38.0 divided by 70, and that in turn gives us 54.3%. Does that make sense to everyone? Okay. So both these percentages, if you add them together, you'll get 100, as expected. Now, what we're going to do is we're going to use a little bit of algebra to simplify how we deal with mass percent and mole percent. And before we get to that point, we really have to understand how do we use mass percent as a conversion factor and how do we use mole percent as a conversion factor. So let's expand on that. So how do we use mass percent as a conversion factor? Well, first things first, we can think of mass percent as the grams of an element or compound per 100 grams of sample. So this conversion factor is really useful to quickly convert between the mass of your sample and the mass of an element, or the mass of your sample and the mass of a compound. Okay, so let's showcase how we can use mass percent as a conversion factor. So we're given that a 35.5 gram sample is analyzed and found to contain 23.5% silicon by mass. Of course, since we've only seen mass percent as a conversion factor, this is implied to be as a mass percent. In all future problems, it'll be explicitly stated. Okay, we're next asked what mass of silicon is present in the sample. Okay, so in turn, we want to go from the grams of our sample And in the end, we want to end up with the grams of silicon found in our sample. So to accomplish this, we're going to utilize our mass percentage as a conversion factor. Let me write this a little more clearly. Now, we know that this sample is 23.5% silicon by mass. So let's try to write this as a conversion factor form. So we know that we have 23.5 grams of silicon per every 100 grams of sample. And this is the conversion factor that we'll be using. Does that make sense? Okay. So then now that we have this information established, let's just execute on that. Okay, so we know that we have 35.5 grams of sample. And since we're going to the grams of silicon, what units need to be on top? Grams of silicon, exactly. So then let's plug that in. We have 23.5 grams of silicon per every 100 grams of sample. The grams of sample cancel. We're left with grams of silicon. I'll show this on the calculator document camera just to make sure we're all clear. So first thing we're going to do is we're going to enter 35.5 times 23.5 divided by 100. And in turn, we get 8.34 grams. So let's write that down. And this is grams of what? We spent a lot of time going from grams to grams of silicon. Again, don't forget your labels. I often find when students start to make mistakes or if their reasoning is unclear, the labels start to disappear and they're thinking, you notice gaps in their logic. So make sure you're including your labels so that way your logic remains consistent throughout. So with this established, let's now take a look at another problem. So I'm going to let you loose on this problem. So a 20-gram sample is analyzed and found to contain 13% carbon. And I'm asking you how many moles of carbon are present in the sample. So it may seem like I'm giving you a problem that looks a little bit different. The only thing I'm asking you that's new in this problem is I'm asking you to go from the grams of carbon to the moles of carbon. And your job is to tell me, well, how do I get the grams of carbon? So take a few moments to work on that. So this percent gram percent grams carbon, that is no. Oh. You just have to add one more. Okay. Are you able to see the right hand back? Everything going on? The first part was good. Now you just go to this step, grams of carbon. Everything going on? Yep, looks good. So let's now come together to discuss. And I saw a lot of reasonable solutions posed so far. My question to all of you is, what units are we starting off from? Grams of sample. So we have 20 grams of sample. Okay, now to go from grams of sample to grams of carbon, we're going to use the mass percent conversion factor. To go from grams of carbon to moles of carbon, what conversion factor do we use? grams to moles? Molar mass, exactly, exactly. Okay. So let's now execute on that. So we have a 20-gram sample. And looking at our percentage of carbon, when we say it's 13% carbon, how many grams of carbon do we have per how many grams of sample? 13 grams of carbon per how many grams of sample? 100. Okay, so let's plug in that conversion factor. We have 13 grams of carbon for every 100 grams of sample. The grams of sample cancel. We're left with grams of carbon. Now for the next portion of this conversion, if we're going from grams of carbon to moles of carbon, what units are going to be on top? Moles. So we have 1 mole of carbon per how many grams? 12, exactly. We are now ready to execute and complete this problem. One moment, let me just zoom into the proper view. Okay, and I'm going to walk over to the calculator screen and we'll enter this into our calculator. So we're going to enter in 20 times 13 divided by 100. Okay, so now we have the grams of carbon, then divided by the molar mass of carbon, which is 12, and that gives us about 0.217 moles, which will round to 0.2 moles of carbon. Why are we rounding this number to 1 sig fig? How many sig figs does our input have? 1. Okay, everyone comfortable so far? Okay. Now, this next sample problem involves remaining mass. So you need to be really careful when you read percent composition problems that you do not make tacit assumptions. Do not assume anything that is not explicitly given to you or that is not implied by the data provided. So what do I mean by that? So we're told that a 15-gram sample is found to contain 14% carbon with the remaining mass being fluorine. And we're asked how many moles of fluorine are present in the sample. Now, there's one key word that I want us to focus on. It's with the remaining mass being fluorine. Okay. Notice how I explicitly told you that this is a 2-component mixture. You cannot assume that unless you're talking about a pure compound, okay? Does that make sense? So the only reason why the percentages add up in this case is because I told you that the remaining mass of our sample is fluorine. This is really important because you'll see problems where this is not the case. Okay, so given that we have a 15-gram sample, okay? And we want to calculate the moles of fluorine. So to calculate the moles of fluorine, what would we need? Do we have a formula to work with? Do we have a formula? No, we don't. We don't. So we don't quite have that path available, or at least going through that path would take a lot of time. But in general, we can get the moles of fluorine from what? From the mass, yeah. So we can calculate the moles of fluorine from the mass of fluorine. Now let's focus on, well, how are we going to do that? This sure sounds nice, but how do we actually execute on this plan? To go from the grams of sample to the mass of an element in that sample, what conversion factor have we used previously? So that gets us to particles. So if we want to go from grams of sample to a component in that sample, is a certain percentage of this mixture going to be fluorine? Yes. So then what conversion factor can we use to go from the grams of sample to the grams of fluorine? Mass percent, exactly. And to be specific here, we're going to need the mass percentage of fluorine. Okay. And now just to complete this, to go from grams of fluorine to moles of fluorine, we'll need the molar mass of fluorine. Perfect, perfect. In this case, I told you that this is atomic fluorine. If I will give you the formula or provide you a name for these mass percent problems. Okay, now we're ready to execute. And let's start with the most interesting aspect. So the mass percentage of fluorine. Okay, so if we know, like if we make a pie chart here, we know that a really, really small percentage, roughly 14%, is going to be carbon. If the remaining mass is fluorine, what's the percentage of fluorine going to be? Roughly 86%. So the mass percentage of fluorine is equal to 100% minus the percentage of carbon, which is equal to 100% minus 14%, which gives us 86%. Does this skill that we've used seem familiar to that when we calculated percent abundance when we were dealing with isotopes? It's exactly the same mathematically. A little bit different on the execution front, but mathematically it's identical. Okay, now we have all the data needed to complete this problem. So we have 15 grams of sample. And we're going from grams of sample to grams of fluorine. So my question to all of you is, what needs to be on top in our conversion factor? Grams of fluorine. So how many grams of fluorine do we have per how many grams of sample? We see this 86%. What does that tell us from mass percent? 86 grams per how many grams of sample? 100. Okay, perfect. One more step remaining. If we're going from grams of fluorine to moles of fluorine, in 1 mole of fluorine, we have how many grams? What was that? 19, yep. Okay, let's now punch this into our calculator. Sorry about that. Okay, let's now punch this into our calculator. So we're going to take 15 times 86 divided by 100 divided by 19. And we should get, in the end, about 0.679. And let me tab out so that way we can see the main screen. So we end up with about 0.68 moles of fluorine. There we go. Any questions on this? Okay. So what I want you now to do is to tackle a similar problem involving percent composition and remaining mass. So a 30-gram sample is analyzed and found to contain 30% sulfur, with the remaining mass being oxygen. And I want you to tell me how many moles of oxygen are present in the sample. Setup looks good. So I see a lot of reasonable answers posed. Everyone's pretty fast at this, actually. So let's now set up here. We're given that we have 30 grams of sample, and we want to indicate the moles of oxygen. So in order to calculate the moles of oxygen, what units are we going to go through? Grams of oxygen. Exactly. Okay, perfect. So now that we have our values in place, let's now figure out what conversion factors we need to accomplish this. So to go from grams of sample to grams of oxygen, what do we need? To go from grams of a sample to grams of a component of that sample. Yep, we'll need to use the mass percentage. And let's be specific here, this is the mass percentage of oxygen. To go from grams to moles, we're going to need the molar mass of oxygen. Note, I indicated this is atomic oxygen, not molecular. Okay, let's now continue on and let's talk a little bit about how we'll calculate the mass percentage of oxygen. So we know we're given in this problem that this compound or this sample is 30% sulfur by mass, with the remaining mass being oxygen, right? So if all of our mass percentages of each component will add up to 100, can we calculate the mass of oxygen? Yep. So we just take 100% minus the mass percentage of sulfur, which is 30%, which gives us that our sample is 70% oxygen by mass. We're now ready to execute on our solution for this problem. So we have 30 grams of sample. And if we're going from grams of sample to grams of oxygen, what units need to be on top? Grams of oxygen. So now we have 70 grams of oxygen for every 100 grams of sample. Okay, and now for our next step, we need to use our molar mass. So we're going from grams of oxygen to moles of oxygen. So what is on top? Moles. So in 1 mole of oxygen, we have how many grams? 16. Okay, we now have enough information for us, and we now have everything laid out, so we can now complete this problem on our calculator. So we're going to enter in 30 times 70, 30 times 70, 30 times 70 over 100 divided by 16. And that in turn gives us 1.31 that we round to 1 mole of oxygen following sig fig rules. Does that make sense to everyone? Okay. So now we're going to take a little bit of dive into more complicated problems. So these are the types of problems that you'd probably see on an exam. So rather than just involving single-step calculations, they involve multi-step calculations using different conversion factors. So let's take a look at this problem and let's try to highlight key features of this problem. So a 2-gram tablet of aspirin is 16.3% acetylsalicylic acid by mass. Okay. In the first part of this problem, we're asked to calculate the mass of acetylsalicylic acid in the tablet. Okay. So thinking about this, we are given the grams of our tablet. Okay. We're given that we have a 2-gram tablet. And we're asked to calculate the grams of aspirin in our tablet. how do we go from our total mass of our mixture or compound to the mass of a component? What conversion factor can we use? What was that? That allows us to go from mass to moles. So looking at this, do we have any information that tells us the amount of aspirin in a tablet? Yep, and what is that percentage representing? Yep, it's representing the mass percent, exactly right. Whoops, let me change the color of the pen. So we have a mass percent, one moment. So we have 16.3% by mass. Okay, so we have all the information we need to execute on this single step conversion. So let's just plug in our numbers now. So we have 2 grams of tablet. And if we're going from grams of tablet to grams of acetyl salicylic acid, my question to all of you is, how many grams of acetyl salicylic acid do we have per how many grams of tablet? How do we convert this mass percent into a conversion factor? What was that? 16.3, yeah. Per how many grams of tablet? 100. Mass percent can be thought of as grams of sample per 100 grams total. So, for example, if we're looking at aspirin, we know that if it's 16.3% aspirin by mass, we have 16.3 grams of aspirin for every 100 grams total of our tablet. And we can just punch that into our calculator really quickly. So 2 times 16.3 over 100, and that gives us 0.326 grams. And since we're doing a multi-step calculation, let me just show you how I would like you to transcribe your values in a multi-step calculation. Using bar notation, we can only report one sig fig. So we're going to carry all of these digits through our later steps, but we are going to report our answer for this step as just 0.3 grams. So I'm going to put this in a box, but I'm going to carry through all of my digits for later steps in my calculation. Does that make sense? Okay. In the next part of this problem, we're asked to calculate the moles of aspirin, acetyl salicylic acid, in the tablet. So in this case, we're asked to go from grams of aspirin to moles. I've provided you the molar mass in this case as a courtesy to showcase this problem. On the exam, expect you'll have to calculate all of your molar masses from scratch. So if we want to go from grams to moles, what conversion factor do we use? What conversion factor do we need to use? Molar mass. In this case, we need to use the molar mass of aspirin, which is C9H8O4. Perfect. We now have enough information to execute this problem. We now have enough information to execute on this problem. So we're going to plug in the mass of aspirin that we've calculated previously. So we have 0.326 grams of aspirin. I'm going to use bar notation to note that this number only has one actual sig fig. And if we're going from grams to moles, what units are going to go on top? Moles. So in 1 mole of aspirin, which is C9H8O4, we have how many grams of aspirin? What's a molar mass? 180. I would recommend on your own calculating this molar mass and verifying that it is indeed correct, because you're going to have to do that on the exam. Okay, let's now punch this into our calculator, and I'll showcase that on the document camera just to make sure we're all on the same page. So we're going to enter 0.326 divided by 180. And that in turn gives us 0.002 moles. So just to showcase this, under bar notation, we're only allowed to report one sig fig. We're going to carry this entire number through our calculations, but if we are asked to report a final answer for this specific problem, we'd report this as 0.002 moles of aspirin. Does that make sense? Okay. Let's now continue on. As you can see, this problem has multiple steps to it. And as a result, we're going to need to carry through our calculations, numbers from previous steps. Okay, let's keep going and let's see what else this problem has in store for us. So next, we're asked to calculate the moles of oxygen in a 2-gram tablet. We're asked to calculate the moles of oxygen in a 2-gram tablet. So how do we go about doing this? We are given, and we've calculated previously, the moles of aspirin, right? We know the moles of aspirin. So looking above, we know the moles of C9H8O4. We know that we have 0.001811 moles of aspirin. And I'll zoom in a moment. Okay, so we know the moles of aspirin, and we're asked to go from the moles of aspirin to the moles of oxygen. How do we do that? How do we go from moles of a compound to moles of an element? What ratio do we use? Formula ratio, exactly right, or otherwise known as the mole ratio. So we're going to need our formula ratio. So given that we have 0.001811 moles of aspirin, my question to all of you is, if we're going from moles of aspirin to moles of oxygen, what units go on top? Moles of oxygen. So how many moles of oxygen do we have in 1 mole of aspirin, which is C9H8O4? How many moles of oxygen do we see? 4. Exactly right. And we can do that in our calculator pretty quickly. So we have 0.001811 times 4, and that in turn gives us 0.007244. We'll use a bar just to note we're only allowed to carry over 1 sig fig. So this is moles of oxygen. You're welcome to report your answer in bar notation if you're carrying it through multiple steps. But if we had to round this, this would be 0.007 moles of oxygen. So this is how we'd report our final answer. Does that make sense? Is everyone able to see this in the back okay? Okay, perfect. So let's continue on. This is really showcasing. I always like to structure problems where you have to show your work, but don't be surprised on an exam if I have you do each of these steps in your calculation, but I don't explicitly ask you for the answer of each step. So I may just ask you to report the value at the end of this series of calculations. I'm just showing you each step just to highlight how you report your answers through multi-step calculations. So let's now continue on. We're next asked to calculate the mass of oxygen in a 2-gram tablet. So we're asked to go from the moles of oxygen to the grams of oxygen. And what conversion factor do we use? What conversion factor do we use to go from moles to grams? Molar mass, exactly. In this case, we'll need the molar mass of oxygen. Okay, so we have 0.007244 moles of oxygen. And if we're going from moles of oxygen to grams of oxygen, How many grams of oxygen are present in 1 mole of oxygen? 16, exactly right. You get that from the periodic table. I think by the time that you're done with this class, you'll have memorized most of the common atomic masses. So we're just multiplying the value from our previous calculation by 16. And that in turn gives us 0.1159 grams of oxygen. If we had to report a final answer, we just report this as 0.1 grams of oxygen. Everyone following so far? We've seen all of these component steps before. We're just asked to apply it in a more complicated example. Finally, we're asked to calculate the mass percentage of oxygen in the tablet. So, given that the mass percentage is going to be equal to the mass of oxygen over the total mass times 100%. Let's see what we know. Let's see what we know. So, do we know the mass of oxygen? Do we know the mass of oxygen?
Yes.
Yes. So, looking at our mass percent, we know we have 0.1159 grams of oxygen. Now, what is the total mass of our tablet? Looking through the problem, what total mass of our tablet did we use? Yep, 2.0 grams. So then we have all the information we need. Oh, not 2.0, just 2 grams. So now we have all the information we need to calculate the mass percent. And I'll do that on the document camera, just for completion. So we have 0.1159 divided by 2 times 100%. And that in turn gives us, after rounding, what do we round 5.7 to? We're rounding to 1 sig fig. That gets rounded to 6. Exactly. So we end up as our output about 5.79%. We can only retain 1 sig fig, so we report this as 6%. Assuming, of course, the only oxygen source is our aspirin. Does that make sense to everyone? Okay. So I'm going to let you loose on another multi-step calculation just so that way you get some practice and we work on some guided practice together for exam level problems. So let's look at this problem. And I'd like you to try and report the responses for this problem. So I'm telling you that ethanol has the density shown above, and I'm giving you the mass percentage of each element in ethanol. And I want you to tell me the mass of hydrogen in 100 milliliters of ethanol. And then I also want you to be able to tell me the moles of hydrogen in 0.1 liters of ethanol. Okay, so given this information, I'd like you to get started on this problem. And then we'll come together to discuss in about 4 to 5 minutes. Questions? Yes. Or you can go the other way and convert the liters to grams. And we're giving the density. To do that. Everything going okay? Everything going okay? Everything going okay? Everything going okay? Mass is just density times. Everything going okay? Okay. So we know the percentage, yes. We know so I'm asking you to tell me the mass of hydrogen. So we know the mass percentage of hydrogen. And now how do you get the total mass? How do you get the total mass of a solution? Like if I told you like the mass everything going okay? I have no idea what this is. Well, we know the mass percentage, right? And how would I get the total mass of a solution? Or in general, how do I calculate the mass of a solution? The mass of the element of the, so that's what mass percent represents. But like if I give you the density and the volume, you give me the mass? Yeah, exactly. So it's just the volume. Are we given the volume? No. We're given the density. Looking at the first question, are we given the volume? It's 0.1 liters, so yes. Exactly. You just need to make sure to convert liters to milliliters. Oh, so convert liters to milliliters. Yeah. Everything going okay? Yeah. Okay. Everything going okay? The setup was fine. Yeah. But let's be specific here. Grams of what? Ethanol. Can you go from grams of ethanol to grams of hydrogen? You have the mass percent. Yep. Everything going okay? Yep. You're correct. You have the mass. Now, you know the mass percent of hydrogen. You go from the mass of ethanol to the mass of hydrogen. So how's everyone doing on this? You need a few more minutes? I'll give everyone about a minute and a half more and I'll walk around and check to see how everyone's doing. Once you figure out the trick, it's actually pretty fast. Oh, sorry. So 1 minute, there's going to be the power of technology is 100 joules. Oh. Everything goes. So almost. So as this was probably going to be the last problem for this supplemental lecture session, let's just remind ourselves that we've seen the chapter on density, right? And we know that if we're given the volume, we can calculate the mass, right? So we know that if we start with 0.1 liters of ethanol, we can convert this to milliliters, and then using the density, we can figure out the grams of ethanol. So we can go from the volume to the mass, right? I like to think about density calculations in terms of unit setups rather than just a formula, because if your units are canceling, there's no way for you to make a mistake in your setup. Now, from the total mass of ethanol, do we have enough information to calculate the grams of hydrogen? Are we given the mass percentage of hydrogen? Yes, yes, we are. Okay, perfect. So now let's talk about each conversion factor that we'll use. So to go from the volume to the mass, we'll use density. To go from the mass of ethanol to the mass of hydrogen, we'll use the mass percentage of hydrogen. Perfect. Now we're ready to execute on this problem. So a key takeaway, what am I trying to get you to see from this problem? Can I integrate density into mass percent calculations and into mole calculations? Is it fair game for me to include density and volumes in these conversions? Yes. So then if you see something like this on later problems or on exams or on your homework especially, know that from the density and the volume, you can calculate mass. And then once you're into the mass, you can do mass to mass conversions. I've seen from your papers you're really good at it. That's the only new thing in this problem is this set of conversions here, which we've actually seen in earlier chapters. Okay? Does that make sense to everyone? Okay. So don't get too freaked out if you see a volume. There'll likely be a reference density for you to use. Okay, so from here, starting off, we have 0.1 liters of ethanol. Liters to milliliters. What units need to go on top? Milliliters. So in 1 milliliter, we have how many liters? And remember, the power of 10 always goes with the base unit. Milli corresponds to what? 10 to the negative third. Okay, let's now apply our density. So then, if we're going from milliliters to grams, what units need to go on top? Grams, exactly. So how many grams of ethanol are present in 1 milliliter? Yep, 0.789. Okay, perfect. And now we're going to apply our mass percentage. So then my question to all of you is, how many grams of hydrogen are there per how many grams of sample? So how do we express our mass percent? How many grams of hydrogen do we have? Yep, 13.1 per how many grams of sample? 100. Okay, now let's execute this on the document camera. So we have 0.1 divided by 1 EE negative 3. So that gives us 100. Now let's look at the next step. We're going to multiply by 0.789, and this gives us the grams of ethanol. And then from here, we're going to multiply by 13. One moment. From here, we're going to multiply by 13. And then divided by 100. And that in turn gives us about 10.3 grams of hydrogen in this sample, which will in turn round to 10 grams of hydrogen. Now, the reason why I said once you figure out this gimmick, the remainder of the problem is actually really fast. Mass mole conversions involving hydrogen are the easiest in the book. Why do I say that? Well, let's set up our conversion map. If I want to go from the grams of hydrogen to the moles of hydrogen, we're going to need to use the molar mass. And given that we have 10 grams of hydrogen, from grams to moles, what unit will need to be on top? Moles. So in 1 mole of hydrogen, we have how many grams of hydrogen? What's hydrogen's molar mass? 1. So that in turn gives us 10 moles of hydrogen. You can also say 10 moles of hydrogen atoms as well. Does that make sense to everyone? So these are the types of questions that you'll see on exam. This question will probably have more parts than just these two, but this was really showcasing you can use density in conjunction with mass percent and mass mole calculations. Density is just another conversion factor at our disposal. Okay, let's now take a look. We will stop here for today. We'll resume with empirical and molecular formula in class on Thursday.